This video is for ELEC 1510 Logic Design. This is Lecture 19, Video 2 on State Assignment, corresponding to Textbook Section 5.7. In state diagrams, states are usually referred to as letters, for example, A, B, C, D, E, F, etc. Sometimes they're referred to as other things, usually it's letters though. In the state table, when we actually design the circuitry, eventually we need to assign state variables to designate the states as binary numbers. So for example, A could be 0, 0, B could be 0, 1, etc. If it had to be a 2-bit number, we would need two state variables, which sometimes we would call something like S sub 1 and S sub 0. This is what we would call the naive state assignment. This is where we take our states and order them, so that's A, B, C, D, and we take our binary values and order them, 0, 0, 0, 1, 1, 0, 1, 1, and we just assign them in a one-to-one fashion. There wasn't really any rationale behind that choice other than it was just simple. Many types of state assignments, other than the naive state assignment, are definitely available, and many of them can lead to more efficient implementations in the circuitry. So that means reduced gates for the logic functions that implement the flip-flop inputs. So let's work with an example state diagram that we're going to implement. This state diagram has 4 states, A, B, C, D. This is a Moore machine where the outputs depend only on the current states, and you can see the transitions labeled there. The state table for that state diagram is given here. This is again the type of state table where we don't yet label the states having their state variables and binary values. This is the type used for state reduction. So you see on the left current states A, B, C, D. You see next states for the inputs, and then you see the output. The output is a 1 only when you're in state D. Okay, so then we would move to the type of state table that we use to actually implement the circuitry, and we're going to use the naive state assignment, which means A is 0, 0, B is 0, 1, C is 1, 0, and D is 1, 1. Again, we call this naive just because it's simple. There was no real rationale behind this choice. So for that being said, the first 2 rows of the state table, S1 and S0, are the state variables, and that corresponds to state A. And then for X being a 0 or a 1, we get next states A, so that's 0, 0, and B, that's 0, 1, and output being 0 in either case. For the next 2 rows of the state table, where S1 and S0 are 0 and 1 respectively, that's state B. The next states are A, 0, 0, and C, 1, 0, and the output is a 0 in both cases. The next 2 rows correspond to state C, that's 1, 0 for S1 and S0, and we get state D, 1, 1, and back to state C, 1, 0, and an output of 0 in either case. The final 2 rows are for the current state D, that's 1, 1 for the state variables, and we get 0, 1, that's state B, and 0, 0, that's state A, with an output 1 in either case. Okay, so this is the type of implementation and state assignment that we've been dealing with since we started the topic of state machines. Now let's look at a different type of state assignment. This will be called the gray code state assignment. And we've already talked about gray code in this class. That's where, as you sequentially move through binary numbers, you only change 1 bit at a time. So we'll use this to assign binary values to the states. A will be 0, 0, B will be 0, 1, C will be 1, 1, and D will be 1, 0. So now, looking at the first 2 rows of the state table, that's where S1 and S0 are both 0, so that's state A. The next state when X is 0 is A, 0, 0. The next state when X is a 1 is 0, 1, that's B. For the next 2 rows of the state table, S1 and S0 being 0, 1, that's state B. The next states for X being 0 and 1 respectively are 0, 0, that's A, and 1, 1, that's C. So now the next 2 rows are actually corresponding to state D because the state variables are 1 and 0 respectively, that's state D. So for state D, when the input is a 0, we move to state B and we output a 1. When the input is a 1, we move to state A and output a 1. For the final two rows in the state table, S1 and S0 both being 1, we move to state D when x is a 0 and output is 0. We move to state C, back to state C when x is a 1 and output is 0. So this is a slightly different implementation. The last type of implementation for state assignment that we're going to discuss is called a one-hot state assignment. So normally the number of flip-flops or state variables is the ceiling of log base 2 of n. So that basically means like you take the log base 2 of however many states you have and then round that up. So like if you had 5 states, the log base 2 of 5 is somewhere in between 2 and 3, so you round it up to 3 and you need 3 flip-flops. In a one-hot state assignment, the number of flip-flops and state variables is actually equal to n. So that means that if you have 4 states, A, B, C, D, in a naive state assignment you would need 2 flip-flops. In a one-hot state assignment you need 4 flip-flops. For each state, only one state variable is ever a 1, or possibly a 0. That would be sort of an inverted one-hot state assignment. Now, one of the reasons why you would want to use a one-hot state assignment is because you can spend more resources on flip-flops and save resources actually on the logic functions that you need to implement the inputs to the flip-flops. So in some cases, you may want to do this just because it's a trade-off of efficiency. Okay, so for the state diagram that we saw back at the beginning of the slideshow, we had states A, B, C, D, and so we're going to assign them in the one-hot state assignment, where A is 0, 0, 0, 1. So as I said, only one of the state variables is ever a 1. For B, it's 0, 0, 1, 0. For C, it's 0, 1, 0, 0. And for D, it's 1, 0, 0, 0. So now you can see in the state table, the first 2 rows are where we have the 4 state variables, and only the very last one is a 1, so that corresponds to state A. Now for the inputs 0 and 1 respectively, we move to state 0, 0, 0, 1, that's A, and 0, 0, 1, 0, that's B, and in both cases the output is a 0. For the second 2 rows in the state table, 0, 0, 1, 0, that's both B. For the input being 0 and 1 respectively, we move to state 0, 0, 0, 1, that's A, and 0, 1, 0, 0, that's C. For the next 2 rows, corresponding to state C, we move to states 1, 0, 0, 0, that's D, and 0, 1, 0, 0, that's C. And for the final 2 rows corresponding to state D, 1, 0, 0, 0, we would move to states 0, 0, 1, 0, that's B, and 0, 0, 0, 1, that's A. And for state D, again, we output a 1. Now what you might see about this is that these logic functions would be pretty difficult to implement by hand, because we would need to have logic functions for S3 through S0 based on the input variables S3 through S0 and X. That's 5 variables, and we haven't talked about 5 variable K-maps. That's actually a pretty difficult thing to do. As you can see, there are lots of possibilities for S3 through S0 that aren't listed here, such as 0, 0, 0, 0 or 1, 1, 1, 1. In the 5 variable K-map, all of those would be don't cares, which can lead to pretty simple implementations in terms of the logic circuitry.